We have Helga from Facebook. Welcome, Helga.
So hi, everyone. I'm here to tell you about two in-house performance analysis tools that we use at Facebook. So performance is a really big deal to this company. And in the last couple of years, we've been really focusing on improving the performance of our products because we believe that it's an essential part of the user experience. So let me take an example with the startup time of the Facebook app. So a few years ago, if you had kind of a low-end Android phone, which happens to be our biggest growth market, then this was your experience starting the Facebook app. Still black. We have a splash screen. It's great. Any minute now. Or not. Oh, did it crash? Nope, back up. Oh, we have a spinner. And the spinner stopped. Like, how did anybody use this thing? I don't think a lot of people in this room would put up with this. And we realized that this was completely unacceptable, like 40 seconds until content. So we really started doing something about it. And today, this experience is completely different. It's a couple of seconds, and then you're good to go. So in addition to startup, we've also been working to improve various key interactions across the app. And we found that it's actually paying off. So for the Facebook app on Android, what once was a declining trend in engagement has now become an increasing trend over time. And performance improvements have been pinpointed as one of the key contributors to turning this around. So performance has had a direct and clear impact on the usage of our product. So similar efforts are underway across our family of apps for the various platforms that they run on. And these include major efforts like Project Lightspeed, which aims to make Messenger the fastest communication app on the planet, and then a complete rewrite of Facebook.com for browsers. And that's our product. But another driver of growth that a lot of you are very familiar with is infrastructure performance. So as all of you know, we have a massive fleet of servers. And so obviously, we want code that's running on these servers to be as efficient as possible. So as we focus more on integrity and privacy efforts at the company, we're making even more demands of our growing infrastructure. So we've set aggressive goals to improve the performance and efficiency of our backend services. And these performance efforts are already resulting in big wins across our fleet of servers. And you'll hear more about one of these programs, service efficiency, at Instagram later today. But with that, let me introduce myself. I'm Helga, and I'm on the performance visualization team at Facebook. Now, we contribute to this amazing performance work that I just described by building analysis and visualization tools that enable engineers to effectively investigate the performance of the various vast and complex systems and software at Facebook. Now, the team mission is kind of broad. It's not focused on a particular part of the stack or a particular metric. Instead, we look at performance holistically, and we try to look for opportunities to generalize tools across different domains and use cases. So we think about performance in terms of the variety of different performance metrics that we measure and track here at Facebook. So we can roughly categorize them into user experience metrics and infrastructure metrics. So user experience covers things like making the apps faster, smaller in size, use less battery, drop fewer frames. And then for infrastructure, we try to quantify server efficiency in terms of utilization, megawatts used, cache hit rates, and so on. And then we use different metrics depending on what part of the stack we're measuring. So for example, to track and measure the efficiency of our web tier, we measure how many users a single standard web server can support, and then work to increase that number. And then for each of these metrics, there's usually a lot of people across the company that work on them in one way or another. So these can be anywhere from performance experts, people whose whole job it is to think about performance, to product developers who really just want to ship their shiny new feature. but sometimes they can't because somehow it made something unreasonably more expensive. So all in all, these are our customers, the people using our tools. But these two groups tend to use our tools in very different ways. So the experts know the tools and the data inside and out, and they're able to tune the views, sift through noise, tune parameters to gain some deep insight into the observed software. But the product developer doesn't have that kind of expertise. Sometimes they're being asked to investigate something in a tool that they've never even seen before. So our challenge is to show them the context that is relevant to them and what they are investigating. And in this talk, I'll show you some ways that we're capturing and codifying expert workflows to make insights more accessible to anybody that uses our tools. Then typically, people will be using our tools with one of two goals in mind. First, there's offense, finding ways to make things faster or more efficient, so identifying some optimization opportunities proactively. And then there's defense, where a metric regresses in some way, the challenge is to quickly and precisely pinpoint the root cause of the regression and then fix it. Now, getting to the root cause can be really challenging at our scale, where hundreds of engineers are working on a product with millions of lines of codes, and you can imagine, and responding quickly to regression is also extremely important. But this gives you some context for why and how our tools are used. But let's actually talk about the tools. So I'm going to walk through a couple of performance investigations using tracery and comparison view. So tracery is our single trace viewer, where you can investigate a single execution in detail and really deep dive into what's going on at any point in time. And then we have comparison view, which looks at performance data in aggregate, which, as you heard from Ben, and as you'll hear, I'm sure, later today in several talks, can be incredibly powerful. So both of these tools are used for a variety of different performance metrics, and each of them has about 1,000 monthly active users within the company, both performance experts and product developers. So tracery tends to be used a bit more for offense, while comparison view is the prime tool for defense. But then users often flow from one tool to the other. I'll start with tracery. Now, at Facebook, we get traces from multiple sources, including local traces captured from the developers themselves. But in production, we collect millions of traces every day from client devices, like phones and browsers from all over the world. And in our data centers, we also gather millions of traces from all of our data centers. And these traces come in through our Canopy tracing backend, which you can read more about in our 2017 SOSP paper if you're interested, or talk to some people in this room. Now, Canopy records and processes over 1 billion traces every day, and they have standardized formats. So even though traces may contain vastly different data, we can reuse a lot of the processing and visualization code. And then we view individual traces in tracery. And here's what you would see. So this is a production trace showing a warm startup of the Android app. Now, in tracery, information in the trace is displayed in so-called analyzers. And each analyzer is a self-contained view into a trace. So displaying some specific information in the trace, like CPU usage in this case, or GraphQL requests. And depending on what type of trace you're looking at, there are plenty of different analyzers to choose from. So we've defined clear APIs for how to build analyzers, and they are commonly implemented by the engineers that are collecting the data themselves. Now, most analyzers display data on a timeline, and there's a single shared timeline for all analyzers. So if I see something interesting in one, I can select that time range and zoom into it and take a closer look at what's happening during that part of the trace. Now, if we expand one of these analyzers to see what's going on for instrumented functions, on the left here, we have threads. Up at the top, we have the main thread, followed by a data thread, which is handling data fetch work. And at the bottom is our layout thread. Now, each of these blocks represents a function executing on that thread. And these nested blocks represent caller-callee relationships. So we think of these as stacks. So this shows us exactly what's happening on each of our threads at any point in time. But one thing that can be really hard to reason about in asynchronous systems or applications is why something is running. So we've been working with one of our infra teams to instrument our frameworks so that we can track how execution flows across threads. So for example, if we click this function here, Tracery will show you arrows that identify work in the trace that's causally related to that function. So here, something called a profile fragment is created. That kicks off a GraphQL request on the data thread. That's connected to the handler, where the response was processed. And since we have the data, we start laying it out with the UI to display it. And finally, we let the main thread know that we're done. So this is one of the ways that we help engineers understand what's going on in traces. And in looking for optimization opportunities or trying to explain why a particular trace is slow, what you're often looking for is some sort of anti-patterns within the trace. So maybe large amounts of data is being retrieved and not used. Perhaps parallelizable work is being scheduled serially. So we want to be able to surface these anti-patterns to users so that they can more easily find interesting things within the trace. Now, if you look at this view, I've already picked an analyzer, zoomed it to a time range, filtered to 3 threads, clicked a particular function to bring up this execution flow, and it's great. But this is something that performance experts are really good at, but we want to make it easier and accessible to anyone. And one of the ways that we do that is with a system we call trace signals. So it's an API which allows users, like our performance experts, to write just a few lines of Python to codify patterns within the trace. So here's an example of a signal that leverages those edges that describe async execution flows. So if a job is executed on through an app's job runner, then that usually means it should be executed in the background. So when a background job posts directly to the main thread, that's usually an anti-pattern, since we want to keep any non-essential work off the main interaction path. And that's what this signal describes. And then Tracery will process this signal and surface it in the UI like this. So warning is displayed at the top, and clicking the warning zooms you into the relevant analyzer, time range, and blocks in question so you can see exactly what's going on. Here, we have the function representing the background job posting to the main thread when it shouldn't. So that was Tracery. I just showed you a couple of examples of what it can do, but it's designed to be generalizable for many different types of traces captured on client devices or backend servers. And for each type of trace, we have configurable workspaces and customizable analyzers. But looking at individual traces in isolation has its limits because, well, individual traces can be outliers. So in production, there are many different devices, different network behavior, user characteristics, feature experiments being rolled out to different populations, you name it. And on the server side, requests get routed to different regions, maybe different load at different times. Some things hit cache, others miss. I mean, the variables are endless. But when you aggregate traces, that's when you start to get a much better picture of what's really going on in production. Which brings us to the second topic for today, comparison view. And this is our aggregate trace analysis tool. As I said earlier, we're collecting and processing over 1 billion traces every day. And as they reach our backend, we apply filters to incoming traces to direct them to so-called trace streams. And we'll have defined different trace streams for different types of traces or metrics. For example, one for Android mobile latency. In these streams, we write code, not all that different from trace signals, that, given a trace, extracts interesting properties from that trace that we want to aggregate. So sometimes this code will even reference trace signals, allowing us to analyze the prevalence of anti-patterns in traces. But each of these pieces of aggregation code outputs some number of rows to Scribe, which transports that data to Scuba, which is our in-memory data store that allows us to run analysis queries at interactive speeds. So you'll hear more about both Scribe and Scuba in talks this afternoon. Now, the comparison view UI sits on top of Scuba and provides a guided way to query and visualize this aggregated trace data based on what metric you're interested in. So a core idea in comparison view, and hence the name, is that you're usually doing comparisons of some sort. So in the UI, you set some population filters that define a treatment group and a control group of traces that you then analyze. And a really common use case for comparison view is defense, investigating regressions. So if we go to the home page in comparison view for a particular metric, you might see a chart that looks something like this. You can see how the metric is doing over time on the x-axis, and how it compares over different app releases, which are the different colored lines in the chart. Now we can see that something happened with version 235. It dropped by almost 15% compared to the previous version. So this is a real regression that happened last month in the Android app. The particular metric has to do with how fast we transition from one story to the next. And we don't want that to lag, otherwise people stop watching. So to investigate the regression, we'll use version 235 as our treatment and version 234 as our control. And here's the full UI for comparison view with those two versions selected. Here on the left are various tabs, and they function similar to analyzers in Tracery. They are self-contained views into some aspect of the trace, aggregated in this case. And like Tracery, depending on what kind of metric you're looking at, the analyzers will be different. And filters you set in one view apply in others as well. So similar to the timeline in Tracery that was shared across analyzers, we don't have the concept of a timeline here, but for other filters, such as population filters, those will apply in a unified way. And this allows you to progressively narrow the scope of the investigation and navigate from one view to another. I already selected an analyzer I'm going to highlight today, which is showing sample Java functions. So when the app is running, if we're tracing, every few milliseconds, we will dump the current call stack on each running thread. And in this view, we have a graph representation of every single stack trace that we have for these two versions of the app, subject to this population filters. So each node in this graph represents a function, and edges between nodes represent caller-callee relationships. So each unique function will only appear once in this graph. So this is different from called trees that some of you may be familiar with, where a function can appear multiple times depending on its position in different stacks. So while tree views are great, and we have them in comparison view as well, aggregating functions together like this in a graph allows us to get a better overall picture of what the total contribution of a function is, which happens to work out really well when you're causing regressions. So the nodes are sized relative to the aggregate cost, which in this case is CPU time, that we estimate based on how often we saw that particular function in stack traces. And the nodes are colored by delta in cost between the treatment and the control. So things that are blue are things that got faster, things in red got slower or more expensive, and things in gray didn't really change. So one pattern that we see sometimes is this. We can go ahead and zoom into what's going on. Bullet-shaped node means that the function appeared only in one group of traces and not the other. And if we look at the function name here, there's a $1 in the name. If you hover over the other one, there's a $3. So this is a machine-generated change in the function name. It's actually just a cost shift. So cost shifts happen quite frequently, and we're able to deal with that in the tool directly by merging the nodes. And now you can see that there's still a slight regression here, but not as much as elsewhere. So we'll zoom back out. So we can see that there are kind of two things that jump out here. There's a blob of things that got faster, and there's a blob of things that got slower. And there's this one node that's a bit more red than the rest of them, and that's a good place to start. So we can select that function, which zooms you in and brings up some details related to that function. And we can see that there's a statistically significant change in CPU time between the treatment and control. So if you follow the stack upwards, this code seems to be related to the video player, and it's spending more time running on the UI thread. Now we could go back and look at individual traces, perhaps comparing one from the control and another in the treatment. And this will take you back to tracery, zoomed into the relevant function. But there's another important clue. So comparison view is integrated with our source control. So we can highlight functions in the graph that were modified in the new version. So if we select that function and bring up the diffs tab, you can see that there's 12 diffs committed between these two versions that are related to this function. And there's the root cause. Now, I've blurred out names and people's photos to protect the innocent, but in this case, someone accidentally disabled video player warmup, which put that work in the critical path, leading to the regression. So bringing together information like this has greatly improved the workflow for root causing many types of regressions. And in some cases, investigations that would have taken hours or days before are solved within minutes. But you might not always get so lucky that it's the first thing you look for. So just as with the investigation I showed you in Tracery, you need to have some sense for what to look for. So after all, we have all these analyzers and different views, and important clues and root causes may reveal themselves in any one of these, depending on what the problem is. So our performance experts are actually really good at these, but we want to make it easier and automatically surface issues from these different analyzers and bring users into views that are already focused on the relevant context. And for that, we have a system we call FB Detect, which analyzes the underlying aggregate data for the different analyzers we have and surfaces that in the UI. And for example, for the call graph view, we regularly scan the underlying data for different metrics and trace populations to find stacks that are regressing. And then we run an optimization algorithm to try and pinpoint the function most likely to blame for the regression. And when the detected regression is significant, we will file tasks directly to the engineers. And here's an example task for a CPU efficiency regression detected in our web tier. So this is PHP code. This regression is blamed to a video encoding function. And for the investigation, the user is provided a link to comparison view. And following that link, the views are already zoomed into the relevant function. Control group has been selected as before the regression. The treatment is after the regression. And the time series shows you the measured cost of the function over time. And you can clearly see it's gone up. The purple marker indicates that this function has a regression task associated with it, which is the one that we just came from. And in this case, the root cause diff that made this particular query more expensive can be found in one of these child functions not too far away. So that was a glimpse of comparison view. And like Tracery, it's designed to work with different types of performance data. It has configurable workspaces and views depending on what performance metric you're investigating. Now, the tool is interactive and supports unified filtering across views, which enables users to progressively drill down as they uncover clues. And it's integrated with external data sources like source control and automated detection pipelines to bring actionable insights to users with as much relevant context as possible. So I've told you a bit about these two tools, Tracery and Comparison View. And before I close, I'd like to just highlight a few takeaways and ongoing challenges that we're working on as we scale these tools out to more users and use cases. Now, the number of users of these tools has been growing quite rapidly. And not every one of these users can become an expert. So there is a need to make performance analysis more accessible, providing right context and actionable insights to developers. Now, we believe that leveraging automation and codifying expert workflows and tightly integrating that with visualization tools is the way to achieve that. And our tools currently cover various different types of performance data in different parts of the Facebook stack, but our coverage is far from complete. So in order to scale to more use cases, we've built these tools out as platforms. So we have over a dozen different teams contributing code and extending our tools using our platform APIs. And most often, these teams will be very familiar with a particular use case and perhaps the data as well, but less so with UI development and trace processing pipelines. So having a platform like this enables them to move fast and get things up and running. So our challenge is to make our tools easily extendable and customizable with clear APIs and configuration options. And lastly, I just want to mention that this talk was exclusively focused on performance analysis, which has been our bread and butter. But one of the exciting upcoming work is to explore how we can leverage these tools and techniques in the context of reliability. Because we believe that troubleshooting failures is not all that different from investigating performance, and sometimes one informs the other. So with that, thank you for your attention. Be happy to take any questions.
Thank you, Helga. We have time for 2 questions for Helga. I saw a hand right here. I'm biased towards the middle.
Yes. One thing I would like to know is you have different blobs that are colored in blue, gray, and red. So from what I can understand, it looks like these are some kind of time that function took, and then you're comparing to the previous version of the same function, and then whether it has gone up or gone down and so on. So are you actually measuring the time of execution for each function and then like have some kind of like history of what it was the previous iteration and so on, or are you doing something else?
Yeah, so in terms of the visualization, it can be any cost that you attach to an entity in the system. It could be hit rates on your cache or the CPU utilization, or in this case, it was the time of functions. So we're estimating the time of the function based on how often we see it and sampled in stack traces. And then through aggregation and like clearly defining population, we're able to sort of average or drop a distribution around the average for that particular function in each and then compare.
Awesome, thank you. I saw a hand, I believe, at the back. No, I didn't. That was a scratch or a stretch. Okay, let's go. Oh, I did. Okay, please.
So can you talk in more detail how you do estimation across populations to handle, for example, the problem of
so I think
reduce variance across them?
Yeah, so how we estimate like cost for sample functions. So I think that's a longer answer than I can provide, given this is the last question before the next talk. So if we could talk offline, I could give you more details on that.
Awesome. Thank you very much, Helga.
Thank you.